So, good morning to all, and welcome to the second talk in the Inspirational Lecture series at the Center for Human Genetics. Now, to the uninitiated, CHG occupies a unique space in the Indian research ecosystem where expertise in rare diseases, with clinicians leading the way in diagnostic and counseling services for genetic disorders, is coupled with basic and translational research in diseases like cancer and diabetes. The lecture series aims to expose us all to eminent personalities from different fields of study with their insights into their work and journey. I would now like to invite our CIT Director, Professor Meenakshi Bhatt, to introduce our distinguished speaker, Dr. A.S. Kiran Kumar, who is a member of the Space Commission, Government of India, and also the former chairman of the Indian Space Research Organization. Ma'am. So,
has formerly served as the Secretary, Department of Space, and as Chairperson. I think I can shout loud. recognition of his contributions, he was conferred the Padma Shri in 2014, the Rajyotsava Award from the Government of Karnataka in 2015, the Sir M. Vishweshwaraya Senior Scientist State Award in 2013 by the Government of Karnataka, a Lifetime Achievement Awards from various bodies, including the Karnataka Science and Technology Academy in 2016, Andhra Pradesh Academy of Sciences, and ISRO Lifetime Achievement Award in 2018, with the H.K. Firodia Vigyan Ratna Award in 2017. He was also conferred the Distinguished IISc Alumnus Award for 2015 and the Bharat Ratna Sir N. Vishweshwaraya Centenary Award by the University of Mysore. This was in its 100th year. This was also the time that Professor Sharat Chandra, the founding society chair of this institute, was honored similarly. So we are very proud of that moment. He has been conferred with many international awards. Special amongst them are the International Von Cameron Award, which was instituted by the Aerospace Historical Society along with California Institute of Technology, and the highest civilian award of the French government, which is the, I don't want to say it in French because it's so difficult, but it is the Knight of the Legion of Honor from the French government. So we're really pleased that you're here with us today. Thank you for honoring us. And please do speak to us about your challenges. Thank you.
Hello. Okay. Good morning to all of you. Wish you all a very happy new year. And 2025 happens to be very unique. Probably many of you are aware that it is the sum of cubes of all numbers from 1 to 9. And it's also 45 squared, like that. There are many interesting things in mathematics about 2025. So thank you very much for inviting me to be part of this particular talk. And what I intend to do is try to take you through the journey of India's space program, and give you a glimpse of how it started and where we are today. So the very first thing that we look at is Dr. Vikram Sarabhai, who is considered the father of Indian space program, said, "We must be second to none in the application of advanced technologies to the real problems of man and society, which we find in our country." And then he also said, to assure its development, India views science and space technology as a crucial apparatus for its socio-economic development. And also, Indian space program is very different. Make it full screen. Make it full screen. Okay.
You can use this front and this back.
This is front.
Yes, sir.
Okay.
That is back.
Yeah, fine. So, 1957 is when humans got a new capability, a capability of going beyond planet Earth. In many ways, it was a disruptive technology which we are all very familiar today, a technological capability of going beyond planet Earth. And this was done by Russians with putting Sputnik into space. And you can imagine India was a fledgling democracy just 10 years into independence, struggling to provide food, shelter, education to its citizens. And at that time, the great visionary scientist Dr. Sarabhai was looking at how this technological capability of going beyond planet Earth can enable India solve many of its problems and provide solutions to various aspects of society. So by 1963, India put its first rocket into space, and starting from practically zero infrastructure, today you have a very self-reliant infrastructure available. And how it all started again? See, Dr. Sarabhai convinced his friends across America, Russia, France, and Germany. And like what we are familiar today, using kits, do it yourself kits, he could get sounding rockets to this place. And for doing that, in convincing his friends, he also pointed out that we have a geomagnetic equator near Tumba, and if you do upper atmospheric research there, it will be beneficial for the entire scientific community. With that in mind, sounding rockets was brought in the form of kits, got it assembled, and you see the church there, that is the place where the first rocket was assembled. See, one of the very early activities what India did was, in 1975, India conducted the world's largest socio-technological experiment. At a time when only 4 metros had the privilege of looking at broadcasting services, India borrowed a satellite built by Americans, moved it over to the Indian longitude, and in 2,400 remote villages of our country, using a technology which you are all very familiar today, a small set-top box and a quarter-meter antenna on your rooftop, you see television programs. You imagine in 1975, equivalent of that was realized, and then using a 10-foot chicken mesh antenna and a black and white television set of ECIL with half a rack kind of front-end equipment, which is now converted into a small set-top box. With that, in 2,400 villages, ISRO demonstrated to the country that if you want to reach out to the entire country, the quickest way is using a satellite which is like a tower at 36,000 kilometer height and can see 1/3 of the globe line of sight. And using that, this was demonstrated. Though Americans were building their advanced technology satellite, it was India which demonstrated that such a satellite can be used for can be used for societal applications. And starting from this, the government was also convinced that this is the way to go about, because alternate that was available was, you have seen microwave towers. Every 1 kilometer you have to put a microwave tower, and we are a 3.25 million square kilometer area. And if entire country had to be covered with that kind of technology, you can imagine not only the time that is required, access, and also the cost. Whereas through the satellite, it is possible to reach the entire country with once broadcasting. But of course, on ground, you had to put many things. Another very interesting aspect that happened at that time was, when the first sounding rocket had to be launched, Dr. Sarabhai had to actually convince the fishermen in that area. For that, he took the help of Bishop Pereira and then told the fishermen, you vacate this place for us to conduct this experiment. One day the country will benefit. Just as though what had been promised became a reality, in 1999 onwards, what we were able to do is, by looking at the color of the ocean through 8 different wavelengths from an orbiting satellite, and through that identifying where the chlorophyll is, and through that the food chain of the fish, identify where in the ocean you can get assured catch of the fish. So you can see the chlorophyll detection. And then in Hyderabad, there is a center called Indian National Center for Ocean Information System. Through them, this information of where the fisherman can get his catch was being provided initially through pagers and that kind of information. But today, with our own navigation satellite, we have taken it to a new level where a small battery operated gadget is fitted into the boat of the fisherman. And this gadget, like our GPS system, locates where the fisherman is, and a mobile in the hands of the fisherman. And also, the mobile does not have any connectivity with terrestrial tower, because once you go a few kilometers into the ocean, no terrestrial tower can reach. But this mobile communicates with this gadget through Bluetooth and Wi-Fi, and an app in the mobile enables the fisherman to show in a video compass mode where he has to go for the fishing. And not only that, it gives him alerts in his mother tongue if the weather conditions are going to be unfavorable in the coming days. And also, many times you would have read our neighboring countries capture the fishermen because they are wading into their waters. So the mobile is now able to tell the fisherman, you are approaching such area, be careful. So now you can see here the example of the most advanced technology of a rocket putting a satellite into orbit, and through that, a person who does not know reading or writing is able to carry on his livelihood. We have actually 11,500 kilometer long coastline, and millions of fishermen depend on their livelihood for that. This activity alone saves to the country between 10 to 15,000 crores a year, because the amount of petrol and diesel the fisherman spends gets significantly reduced. And this is one of the very interesting developments that happened. And of course, one of the key things was also in the earlier era, earlier decades, super cyclones used to take away lives of tens of thousands of people. But today, by virtue of the geostationary satellite, looking at the cloud pattern, temperature and humidity, you are able to tell well in advance where a cyclone, super cyclone, is going to hit the coast, and disaster relief agencies are able to evacuate and save lives. So you have seen in the recent decades, the loss of life has been reduced to single digit numbers. And then in terms of space application itself, your ability to orbit around the Earth helps you look at a whole lot of things: agriculture, environment monitoring, land and water resource management, ocean application, even ocean applications to the extent of providing inputs for weather monitoring, because using the sensors on the satellite, you know what is the wind, ocean wind vectors, and then ocean surface temperature, which all go into the model. And then similarly in communication application, telecommunication, broadcasting, telemedicine, probably you're also familiar that in the early 70s, if the information had to be passed on, people had to go to Central Telegraph Office and book a person-to-person call. And if you are lucky that day, you will get the connectivity. But today, a small gadget which you are carrying in your hand can link you to anybody in the world. Similarly, in NAVIC application, India is also able to provide equivalent of GPS with only a 7 satellite constellation covering an area about 1500 kilometers beyond our border. And this data is also being used for, very soon going to be used for providing toll-less traffic thing and many such applications. And train services are using this capability for providing real-time information about the trains. And then disaster monitoring, of course, cyclone, flood damage assessment. And beyond that, as the country's capability kept growing, and because of the very friendly neighbors we have, strategic application also becomes an essential requirement. So during this period, if you look at what all has been achieved, we have put more than 99 launch vehicles, 129 satellites, not only ours, about 440 satellites of 34 countries has been done using our launches, 18 student satellites. We started with a simple satellite launch vehicle, grew into ASLV, PSLV, GSLV, etc. We'll see some more details later. And then one of the early experiments that was also done was a space capsule recovery experiment, where an object which was orbiting Earth came back and then got picked up. One of the key things here is when you come back into the Earth, entering into the Earth's atmosphere, because of the friction, the temperatures at the surface can get into thousands of degrees, So you need to build special material to survive such conditions. And PSLV happens to be one of the very reliable launch vehicles across the globe, and it has done many activities, putting 104 satellites in a single launch, then doing the first time taking missions to Chandrayaan, Mars, etc. A whole lot of things. And today we have done more than 60 missions using that. And while you built all these capabilities, it was also necessary that in area of science and technology, you know that if you want to remain active, you need to challenge yourself and do more and more challenging activities. While we had built satellites which could be taken up to 36,000 kilometers for geostationary, going beyond that, taking it to farther distances was one of the challenges. So Chandrayaan 1 was such a thing which was done in 2008, where you traveled a distance of up to 380,000 kilometers. Here again, the way it was achieved is very interesting because we had a limited launch vehicle capability. The amount of weight it can carry is limited, but within that, we were trying to put a satellite into this. So we adopted a scheme where the launch vehicle itself put the satellite into an elliptical orbit, and then satellite, by using its own fuel, keeps on increasing the orbit to progressively higher and higher altitudes, and then finally when it comes very close to moon, you reorient it and get captured on the moon. And this also was actually attempted for the first time, and we had to adopt it simply because we did not have the capability of launch vehicle carrying a satellite directly to the lunar trajectory. But then what happened in this is also an indication that by 2008, man had landed on the moon. A large number of probes had touched the surface of the moon. But still, Chandrayaan 1 gets the credit for discovering the presence of water molecules on moon, and also the process which is responsible for water molecule formation was actually, the credit goes to this satellite. And you can see here that though you started an activity much later in science and technology area, it is never too late. You can always do something which others have not done. This is another interesting example of that. And lunar exploration program itself, it made detection of hydroxyl and water molecules present on that. And then it was also an experiment where more than 11 countries participated along with us, and it was an example of international cooperation. And of course, Chandrayaan 2 and 3, I'll touch about it a little later. And some of the salient results of Chandrayaan 2 was also the first global observation of argon, and we have the sharpest ever imaging capability. Orbiting moon, we can take images of 25 centimeter resolution. In fact, it was this ability which enabled us to successfully land in last year, and because of certain problems we encountered in Chandrayaan 2, we could not complete that mission. I'll touch upon that a little later. And also again, when the Mars orbiter mission was done, India again was the envy of many other space countries, because in its maiden attempt, we were able to put an object, reach Mars and get into the Mars orbit. If you have to appreciate the complexity of this, in 2013, in November 5th, when the satellite was launched, the task cut out for the satellite was travel a distance of 60 crore kilometers, 600 million kilometers, over a period of 10 months. And at the end of that period, you imagine in space a cube of 50 kilometers. So after this much of travel, the satellite had to be inside that cube on a specific day and time, 2014, September 23rd, morning 7:30 a.m. to the second. If in that second, if the satellite was not inside that cube, we would not have been able to put the satellite into the Mars orbit. What all could have caused problems to that? Even many of you are aware, radiation pressure, sunlight falling on the satellite can produce force which over a period of these 10 months can deviate its trajectory by tens of thousands of kilometers. So you need to keep communication with the satellite. You need to make sure that it responds to what you are doing. And even there, it takes almost 14 minutes for the signal to reach the satellite. The time you give a command, many of you, when you start your laptop, it takes few hundreds of milliseconds. You start feeling fidgety. My system is very slow. You can imagine the plight of the people sitting in the control room. The command they have given reaches 14 minutes later, and by the time you get back the information telling everything is okay, it's almost half an hour. But anyway, those are the challenges of doing activities like this. And again, here, many times you would also have be clear that if you were to learn everything through your own mistakes, one lifetime may not be sufficient. But if you can learn from others' mistakes and solve, you can be called smart, and then they take advantage of that. Mars example was like that. We were the first to achieve in its maiden attempt because we could get some clues on what problems had occurred in others and took advantage of that development. And again, these are some of the results of that. While the original design was for only 6 months of operation, satellite lasted for 8.5 years, and then we got a whole lot of information from this particular satellite. You can see some very interesting images, upside down penguin type shape in the second image, and the moon of the Mars is being captured using this satellite. And we also built a satellite called AstroSat, which even today happens to be the highest angular resolution in a specific wavelength. While James Webb Telescope, etc., or even Hubble is there, this satellite has the credit for, in a specific ultraviolet region, it has the highest angular resolution and the highest sensitivity. And this has provided a whole lot of information to the researchers in the country. And space technology itself, if you look at in totality, you are able to cover a large number of observation using the orbiting satellites. You can create a digital elevation model and then navigation for positioning information. And through computing system, you can bring in a whole lot of applications. All that, and how it was brought into reality was, see, many times what happens is you can have a capability, but then building that capability and reaching to the user and make him realize that he can do an activity which is much faster, better, is always not very easy. See, normally what happens is if somebody comes to you and tells what you are doing can be done in a very different way, first reaction would be, who are you to tell me? I know my job better. But then it takes a lot of convincing to tell. And here, actually, Honorable Prime Minister had asked us to organize a 2-day event in Delhi where all the secretaries of states and central governments were brought together, and then how space technology can be usable in various departmental activities were showcased. At the end of the 2-day event, Honorable Prime Minister himself spoke extempore for 45 minutes, telling the secretaries how space technology can make a difference to the activities that the government is doing and governance. And as a result of that, a lot of things change. And this is just to give you an example how over the last 40-45 years, ISRO has been trying to make use of, bring space technology to the users. Forest Survey of India started adopting way back in 87, Ministry of Earth Sciences in 99 for fisheries, etc. And then Ministry of Agriculture, about crop forecasting, and Airport Authority of India, like that. And then international cooperative missions. See, the space also, if you can cooperate with others, you can take some advantages. We work with French and others for building. And true to our own tradition, the knowledge and the skill you acquire should also be beneficial to your neighboring countries. And this was again the Prime Minister's initiative to provide a communication satellite capability to our neighboring countries, Bangladesh, Bhutan, Maldives, etc. And this satellite provides both broadcasting and
game changer of the Indian space program. Successfully operationalized after 3 developmental flights in 2019, LVM-3 is a geostationary launch vehicle of the third generation. The second operational flight is commercialized to an international customer, OneWeb, an indigenously developed 630-ton launch vehicle capable of placing payloads of up to 4 metric tons into geosynchronous orbit (GEO) and 6 metric tons into low Earth orbit (LEO). The vehicle has 7 consecutively successful missions, handled GEO, LEO, planetary missions, and commercialized in a short period of time. Game.
And of course, we used the same LVM-3 for the Chandrayaan-2 mission. In Chandrayaan-1, we had a moon impact probe which went and crash landed on the surface because it was an uncontrolled descent. In Chandrayaan-2, we were attempting to put a lander or soft landing on the surface of the moon. But here the challenge was we were building for the first time an engine which required throttling. Throttling means if you accelerate or decelerate, its speed should change, thrust value should change. Because till that time, the rocket engines we had developed, once you start operating, it delivers a fixed thrust because that was adequate for all the activities we were doing. But when you want to do soft landing, you need to make sure that the engine is able to change its thrust level, because as you keep coming lower and lower, the fuel is getting exhausted and the same thrust value can give higher acceleration. So you need to reduce it. So we were building an engine of that capability of throttling. And obviously, when you are developing some new capabilities, certain things can go beyond your expectation. And in Chandrayaan-2, we came very close, just within 500 meters of achieving the target, but it did not happen. But Chandrayaan-2 also carried an orbiter which produced very high resolution imaging capability. I'll show you how it helped in a subsequent thing. So here, starting from at a height of about 30 kilometers, the satellite or the lander was being brought down slowly and then landing on the surface of the moon. When we were at a height of about 500 meters, certain mismatch between the expectations of the engine performance and the logic that was used for controlling the system resulted in the crash landing of that. Instead of less than 1 meter per second, it went almost at 40 meters per second. So that's how it crash landed. But then between 2019 and 2023, we were able to do all the requisite corrections, understanding, development, and then made sure that last year on in 23, when this soft landed on the moon, India became the first country to put an object in an area where nobody else had done. And this, of course, makes use of, again, some modifications were done in thruster. And here what you need to appreciate is when you are doing any activity, the amount of resources you have which is available in reserve decides what kind of designs you make. In the first one, the amount of fuel we could carry was limited, and then also the knowledge about the starting point and the end point was also limited because very high resolution imaging data was not available to us. We had to depend on international collaboration data. So here you can see, starting from a height of 31 kilometer, the object starts descending and progressively it comes down, and then at about, when it reaches a specific point at a height of about 1 kilometer, you take the image of the area, match it with a corresponding image. So we were able to generate using Chandrayaan-2 the entire stretch of 780 kilometers at 25 centimeter resolution data. So we knew exactly the surface, and in Chandrayaan-2 we had identified a 500 meter by 500 meter area for touchdown, whereas in Chandrayaan-3 we had a 4 kilometer by 2 kilometer area where any 100 meter circle you could come down and safely land. So that was the advantage. So your end point, you have a larger margin, we could carry more fuel, and we also built in features which could be tested in orbit, so that many times when you have built a new thing, if you are able to test it in actual operating conditions, its performance can be assured. If there are changes, you can correct your algorithms and make sure the modifications can still be absorbed in the performance. So we were able to do all this successfully in Chandrayaan 3 and then landed, and probably many of you would have seen large number of videos and images. We had the rover, Pragyan rover, moving on the surface of the moon, and then it also carried many instruments. One is what is called as the Langmuir probe, and also temperature on the surface of the moon. Then you had a seismic activity monitoring, alpha particle X-ray, and a laser-induced breakdown spectroscope. That means you fire a laser onto the surface, and whatever evaporation happens, do the spectrum, and from that you can identify what molecules are there present on that. And then in addition to that, we were also able to do additional experiments because we still had large amount of fuel. So we actually made the lander go up again and come to another place. So these are all technological demonstration which will help in our future activities. And similarly, the orbiting propulsion module was brought back to Earth, and of course our idea was to actually make it enter the atmosphere and get in, but we did not have enough fuel for doing that because these were all additional experiments that were conducted. But anyway, it is no longer a debris on moon and it has come back to an Earth's orbit. And this gives you an indication of what all goes behind the actual creation of a Chandrayaan 3 type of system.
The Chandrayaan 3 spacecraft consists of a propulsion module and a lander module with a rover accommodated inside the lander. The propulsion module and the lander module are stacked together to form the integrated module. 6 modules were realized during Chandrayaan 3 project life cycle, out of which 3 were flight modules and 3 were special test modules, namely the integrated cold test, integrated hot test, and lander leg drop test modules.
The main function of propulsion module is to carry the lander module from launch vehicle injection till lander separation. The propulsion module was made ready for further integration with lander module.
A 6-wheeled rover is accommodated inside the lander, which would be deployed onto the lunar surface post-landing. Rover solar panel deployment and illumination test, rover standalone EMI-MC test, vibration test, thermovacuum test, and mass property measurements were carried out. All tests associated to rover were successfully completed and the rover was made ready for further integration onto lander. After integration, detailed IST, sensor level alignment, and EMI-EMC tests were also carried out before shipment to ASTE Bangalore.
A new facility was realized at SDSE Shar for conducting the IHD. Craters and boulders simulating hazards during landing. A total of 20 tests were successfully conducted, which include 6 dry runs, 8 static tests, and 6 dynamic closed-loop tests. The lander leg drop tests were carried out to evaluate the energy absorption capability, strength and stability aspects of lander legs during touchdown. A new facility was realized at iSite with a test bed with flat and 12-degree inclined crop surface. Detailed tests were carried out at damper level, single leg level, simulator level, and QM structure level for various touchdown velocities on flat and slope surface and on lunar soil simulant and hard surface. A total of 15 drop tests at simulator level and 2 drop tests at QM structure level were conducted successfully. The objective of lander is to demonstrate safe and soft landing on lunar surface. Major elements of lander include sensors, after the completion of thermal elements in the rover compartment, the rover was assembled onto the ramp using 3 hold-downs. Detailed assembled mode IST was carried out, followed by mass property measurement, thermo-vacuum test, solar panel assembly, and illumination test, EMI-EMC test at CATF iSite. This was followed by pre-dynamic deployment of secondary rover ramp, primary ramp, and rover rollout from lander, and payload deployments such as ILSA and Ramba, chased, and the lander was made ready for further activities. Once the lander module was ready, it was stacked over the propulsion module to form the integrated module. EMI-EMC, vibration tests, acoustic tests were carried out. Final finishing activities such as MLI sealing, Chandrayaan-3 spacecraft was made ready for shipment to spaceport at SDSE Shar.
So that just gives you a glimpse of what all goes behind a successful mission. It's a lot of hard work and dedicated effort, and still it does not assure you a guarantee that everything will go right at the end. And we also did last year another mission called Aditya, where a telescope is going to a point called Lagrange point. This is a point between Earth and Sun, such that you don't require much of fuel to keep the satellite in that position. So you can imagine when a total solar eclipse occurs, on the ground there are very few places where you can observe the total solar eclipse, and that too for few minutes. So scientists spend a lot of time and effort establishing their equipment to look at the sun with the photosphere covered for those small duration. But then using this kind of a system, you can build a coronagraph where you can look at what is happening beyond the sun's photosphere 24/7. So this satellite is doing, actually it has completed 2 orbits around a imaginary point. Unlike other orbiting satellites, this satellite orbits an imaginary point called Lagrange. And what we just a couple of days back, the data from this has been released to the scientific community. So this roughly we are 1.5 million out of 1.5 million kilometers distance. We are about 1% closer to sun. Having done all this, now the government that India needs to get into human space activity, and then originally the plan was by the 75th year of independence we should have put Indians around the orbit, but then COVID and a whole lot of things delayed substantially both the government's ability to support the program and also the whole lot of the supply things, material being available. So now what is going to happen is this year you will see two of the launches which will be before the actual humans get in, uncrewed orbits, I mean, launching will happen. And then after two successful uncrewed mission, we will have the Indian astronaut going in our own Gaganyaan program. But in the meantime, one of the astronaut is also likely to travel in the an American system earlier in the first half of this year. Because this just gives you a glimpse of what is there in the Gaganyaan itself.
Hamara Gaganyaan. The year
कोई भी हो सकता है, वे अंतरिक्ष में जाएंगे, हाथ में तिरंगा झंडा लेकर के जाएंगे.
Many challenges like pad abort test to rescue the crew during liftoff, drop test to qualify crew module, parachute test for safe descent are successfully complete. Environment control and life support system, space food and medicine, and many are in the verge of conclusion. A few test vehicles, unmanned and robotic missions are planned prior to the human flight. सारे जहां से अच्छा हिंदुस्तान हमारा, सभी हिंदुस्तानियों को हमारा
Yeah, another interesting thing you saw is just we have, because of the resources constraint, we started making use of the fourth stage of the PSLV for conducting experiments which could help us learn about space station. And also just recently, for example, a few days back when the launch took place, we have 25 experiments being conducted in this orbital platform, what is called as PSLV orbital experimental module. And you see an experiment called CROPS. It was flown in the C-60 mission of POEM. Cowpea was chosen based on ground trials on a variety of seeds due to shorter germination time. After launch and main satellite separation, POEM platform was lowered to 350 kilometers orbit, and all the system parameters are okay. On the fourth day, sprouting of seeds from the enclosed tissue strips was observed. So you can see here the this is actually an experiment carried on POEM and over last 7 days, and you will see the sprouting of the seeds and the leaves coming out in this. So in the microgravity conditions, just mimic trying out. So such activities can be done, and actually about 25 different experiments. In fact, there's another university which was trying to do even probably spinach. We still have to get the results of that. But this experiment was part of ISRO's effort only. So we immediately have the results available. And then looking beyond that, now you can see space economy, why space is important, etc. If you see, as the country's capability grows, see, like I said, 1947, when we got independence, we were probably way down in the economic ladder. Now you have reached fifth and aspiring to reach number one by 2047. And then as you keep moving up, you need to have capabilities in different domains. And space is a domain where a lot of private entities are getting into the action. Like in any other sphere, man conquered land, ocean, airspace. Now he wants to conquer space itself. Space tourism, space adventure, space exploitation, whole lot of things. And if that has to happen, a country which had an ability of building launch vehicles, satellites, and application, should it not get significant pie in the space economy? Space economy is expected to grow into $1 trillion economy, and that's where the government has made a huge change in the way space activities are going on. A lot of space startups startups are coming and private entities are getting into this action. And then by 2047, some of the thing that is expected is by 2035, India will have its own space station called Bharti Antariksh Station. And by 2040, India has plans to land humans on the moon and bring them back. And life beyond planet Earth means a whole lot of activities in different domains, and all of that requires a larger participation from the people, from the various sectors of the country. And then I'll just end with a few points. See, one of the successful development that has happened in the country is because Sarabhai's vision for enabling India was to leapfrog into the future through the adoption of appropriate technologies. That means what ISRO demonstrated is use whatever technology that is accessible to you. Using that, try and address problems you are facing and solve them and provide solution. For example, in 1975, when satellite instructional television experiment was conducted, it was demonstrating the ability of using satellite technology for reaching out to a developing countries' communication, broadcasting, and also weather monitoring system. And then between 95 and 99, India had the privilege of showing in the civilian domain highest resolution imaging systems. As a result of that, we had about 18 ground stations across the globe receiving this data. Mars orbiter, you saw that demonstration in the very maiden attempt achieving the Mars orbit insertion. Astrosat, again showcasing that in a particular wavelength you have a sensitivity and angular resolution better than anybody else in the world. And similarly, 104 satellites, when it was launched, it was a record of sorts. And what is leapfrogging as a concept? If you want to reach a particular height, you have to prepare yourself, generate enough momentum by running. What if that much space is also not available to you, but still you want to climb, you want to jump? Then, like a frog, you conserve all your energy, crouch, and make one leap. So that's the leapfrogging. So India, starting from its independence, when you were based on lot of external rule, your strength and was very limited, how to take advantage of the intellectual capability of the people. So leapfrogging was one technique. Another very important aspect what Dr. Sarabhai was emphasizing was the important ingredient for satisfactorily meeting the challenge of the changing environment is not experience, but ability to learn. It may look very counterintuitive. In fact, what he had done when he was given the task of running ATIRA, Ahmedabad Textile Industrial Research Association, he put an advertisement in the paper telling people with experience need not apply. See, it looks counterintuitive, but you just think about it. When do you need experienced people and when do you don't need them? If you are already clear what you require to do, things have been established, then you need people with experience to make sure it happens. But if you are solving new problems, you are facing new challenges, then experience can many times become a deterrent because you have some preconceived notions of how you are doing. So the idea should be not experience, but your ability to learn and make things happen. So experience is less relevant than knowledge and the ability to learn and innovate. In fact, some of these thoughts, if you see, are very interesting, and probably that is the reason why ISRO was also able to, with the kind of culture that evolved. And technology is not an objective to be aimed at, but a tool to be used for the benefit of common man. This again, India is the only country which started space program for non-military application. But today, of course, as you grow, your need to use it for military anyway will come. But then primarily it was evolved for non-military applications. Okay, I think I'll end there. Sarabhai's vision on the development of space technology and its extensive application for betterment of society continues to be the guiding light of the space program. Thank you very much for patient listening. I'll be more than happy to answer any questions you may have.
Well, thank you so much for literally a talk that was out of the world and truly lived up to its billing as an inspirational lecture. Thank you so much. So, if you're amenable, I'd like to open the stage for a few questions, especially from students. Oh, okay, no, not
Anyway,
anything.
you can go ahead.
Anyone can.
It'll
but you can
break
start.
the ice.
Yes, but
Normally,
please do
what
start,
happens is,
and
unless somebody asks a
I
question,
would really encourage students to ask.
Sir, very inspiring lecture. You must know some of this. How are we going to leapfrog our launch vehicle capability to generate more thrust? What are the things?
yeah.
Thanks.
See, currently, whatever capability we have, particularly in terms of the weight, you saw about 10 tons to the low Earth orbit, etc. So we have started the work on next generation launch vehicles, which is supposed to give us something like 30 tons and then up to 80 tons. So the work is in progress. What you need to appreciate here is, see, the way we started the activity and the country's economic strength. See, if resources were available, probably by now we would have done much more. But then the country, the government, each government has its hands full of prioritizing and providing resources. And because of that, many times what happens is, though you have idea of what you can do, the facilities you need to establish, etc., takes the backdrop, and current operations becomes important. So much of the development has been constrained not because of inability of the system, but inability to provide required resources. So now things are changing. So, but targets are also being set very high. So you can see between now and 2035 and 2040, carrying human beyond planet Earth means life at stake. So all the necessary quality control ensure essential. But this is on right now. The government has already made these choices. So depending. Okay. Okay, see here what happens is, if you take any two body system, Earth and Sun, by mathematically you can show that if you are at certain specific points called Lagrange points, there the amount of energy required for that satellite to be kept there is minimal. You do, otherwise in any other place what happens is, once you put into orbit, it will remain there, but there are other forces which will keep disturbing the orbit. So as a result of that, you have to keep correcting that orbit. So here in this particular case, if you put exactly at the Lagrange point, probably you don't need anything. It will simply be carried between, because of the forces between these two objects, it will be there. But if you put exactly at that point, you have a problem. On one side, you want to look at Sun. Now, if you are looking at Sun from Earth, if you want to receive data coming from the satellite, Sun is in the field of view of the antenna. So like in the daytime, you cannot see stars, not because they are not present, but because your eye is flooded with sunlight and your ability to adapt to that other light is not there. So what is done is, satellite, instead of being kept there, is moved away so that the antenna's field of view does not cover sun. So it's about 2 degrees, etc. So you move the object away. Since you move it away, it cannot remain like that. You have to make it go round. So this is called a halo orbit. Satellite, one side is looking at Earth for communication, other side is looking at Sun continuously. So because of that, you have to do. And then since it is a non-ideal point, some variations are going to happen. So you have to make sure that you have to correct that small errors. And there the orbit period is almost 6 months. That means it will go through that complete path once in 6 months. So we have completed two such things. And also you can imagine earlier we were actually putting the objects into some other celestial body. But here, since it is not such a thing, the whole lot of computations, understanding is all for the first time when it is happening. You can always get into some issues, but we were able to successfully do that. No, microgravity lab, for example, I showed you the poem. Poem is going to last for 6 months. So that means those who want to conduct experiments up to a period of 6 months, we can put it in the poem. In fact, there is a university in Mysore which is trying to evaluate the performance of some particular drug, what is going to be its behavior. Like that, there are a lot of experiments which are being planned, and poem itself can provide you opportunity for conducting microgravity experiments. And between now and actual moon orbit, our Bharti Antariksh station, and also reaching to moon, there will be a whole lot of launches and platforms. All of them can in principle carry experiments of different categories. In fact, today the work is going on of making more and more people biology experiments and other experiments. In fact, you can also see, to provide an appropriate environment for the human to survive, you have that environmentally controlled uh, system being realized. So there's a whole lot of activity. How much carbon dioxide is there? What toxic material is there? You have to measure. You have to remove that. Whole lot of things are going on. There, somebody is there.
Good afternoon, sir. Sir, my question is how biotech sector can contribute in participating in space economy, particularly in the direction how space exploration is heading towards.
Yeah, if your desire is to send humans beyond planet Earth, there is a whole lot of activities which you need for enabling that him to survive itself or her to survive itself. That is one. But then beyond that, like you saw, the growing of some things itself. Tomorrow, if we are going to land on moon and create habitats there, or create habitats in other planetary bodies, etc. So there is a whole lot of activity which you can imagine. It's actually limitless in that sense. But then how it will happen depends on what work gets done, and then how it gets selected into the actual operations. Otherwise, in terms of ensuring life beyond planet Earth is where all the biotechnology is coming in. Yeah, there is one here. Yeah.
See, in any enterprise, there are parameters which can defy predictions. So, in what you have talked about in its entirety, in its broadest sense, even if you're most well prepared, what is it that you fear most?
Yeah, this is where what you are saying is very correct. See, what you can do is based on your knowledge of things, various parameters which can go to the extremes under which you have to design your system to perform. I'll give you the example. Our own PSLV launcher, it had done almost 50 successful launches. But then in the next one, we had our heat shield not opening. Heat shield is a system which is provided to actually protect satellites when it crosses the Earth's atmosphere. That extreme heat not reaching the satellite. So you have a shield. But that shield should be removed for the satellite to be ejected into the orbit. So now we had done successfully almost 50 missions. But in the next mission, the whole combination of parameters went to one extreme. Suppose there are 10 parameters affecting that. You have got the peak and the 3 sigma limits. But if all of them are aligned, you have got the ideal thing. But if they misalign, then you don't get performance. So in this particular case, so many of them were at the extremes. So that condition was not suitable for the system to operate. But then based on that, now we revised many of things, and now we can tolerate much larger error margins. But coming back to the point, what you are saying is you are always finally limited by your knowledge and then your ability to provide for the extremes of that particular parameter. This is where resource comes into picture, efficiency of operation. Suppose you have unlimited resources, then you can extend these limits and then make sure that your design works even for that limit. But never that is the case. Your resource will be constrained. So you have to make a choice. So majority of the time what happens is that engineering judgment happens, and if things remain within that judgment, you succeed, otherwise you will fail. So there is no solution to that. The only other way is, can you build intelligence into the system so that it keeps learning based on what it is encountering, but then you should build so many capabilities to deal with those problems. Anyway, that's a challenge in itself. You wanted to ask?
So my question was like there are several research observatories like LIGO and JLSU coming up for gravitational waves as well as dark matter. Is ISRO planning any space probes like for the Indian Indian space station that's coming up? Are there any like dark matter or gravitational waves observatories planned?
Okay, what I would like to say is, the ISRO's job is to use space technology for any activity that country wants to do. Now, if LIGO science experiments are being thought of by scientific community, whatever is required from the space segment will be enabled. So ISRO itself will not plan a LIGO experiment. So ISRO's task is to provide space technology for countries' activities. So what it is trying to do is, initially obviously not much of familiarity is there, you are doing various activity, but by now you have already reached a stage where there are enough participants in all areas. See, for example, just today there is a discussion going on by a group of scientists to decide what kind of exoplanet studies have to be done. So they are discussing, because the government also, you can see, wants to know how many people are going to use this data, what are they going to do, is it worth doing, should the government spend or not. So that is where it is not ISRO which is going to decide whether it will be done, but ISRO will be tasked to provide necessary support to make it happen in space. Whether it is science, technology, application, strategic, in all those areas, the task for Department of Space is enabling the country. So if you want to come up with an experiment, you have to convince and then come up with a proposal which passes through the various mechanisms and goes ahead.
Kiran Kumar.
Yeah.
One interesting experiment that could be done, especially for these long duration flights, would be, I think, do a short term lymphocyte stimulation experiment which will help the cell to grow in space and keep interesting controls. One is, of course, the astronaut's own blood at the starting point to obtain base level data, and then have another control from a, let's say, Fragile X chromosome breakage syndrome, and measure the extent of chromosome breakage that could occur during space flight. That may have some usefulness for long-term flights.
Yeah, definitely, sir. A lot of these things are now getting, because more and more diverse scientific community, including medical field, people are getting involved. So we will have opportunities, because a large number of launches are going to take place. Even I said that fourth stage itself, instead of earlier, it was simply coming back. Now we have added a little bit of power and other capabilities. So instead of simply staying there, it is providing us a microgravity platform. So that's what the poem experiment you saw. So like this, we are trying to increase our ability, but the experiment itself, what to be done, how to, that probably will need experts from appropriate area to both design and then make it happen. We'll definitely take your point.
How much is the industry contributing to this?
Yeah, if you look at that, sir, if you see in terms of launch vehicle, actually all the big activities are actually done in the industry, but with our supporting hand, etc. In fact, there are more than 500 companies which have been providing support to various activity. Unlike any other organization, ISRO has been able to actually enable a large number of companies in the country and also make them deliver the results. So that is the difference what ISRO has done in today. PSLV, all four stages are being done in the industry, and then SSLV, we are expecting the entire thing to be realized in the industry itself. But there are also companies, new startups which have come, who are building their own launch vehicles and satellites, etc. Already more than about 200 startups are there which have entered into the space activity. So India is really moving very fast.
Will that be controlled by the ISRO or by the Space Commission?
No, actually, what government has done, there is an entity called InSpace, Indian National Space Promotion Center, which has the responsibility for giving authorization and regulating the activities by these. But that is also under Department of Space. So InSpace is part of Department of Space. Then Department of Space also has a New Space India Limited, which will do all the commercial activities of providing launches, providing satellite services, etc. So the government is enabling this to happen through private enterprise, because there is no point in government spending money for those activities which can be commercially done. Yeah, there is probably one
Okay,
last.
maybe one more we can.
Sir, thank you for this inspirational talk. I was just curious to know how ISRO deals with space pollution and space debris, and does it affect the launching of those vehicles? Those things?
Probably if you had watched the recent launch, it was delayed by few minutes. Now why the delay was done is because there is what is called as a collision probability analysis which gets done before you send any rocket into the space. You don't want any object in space within 500 kilometers of your trajectory. So if the time at which you are launching results in some object in space coming within this vicinity, you change your timing. So that is within certain limits, of course, it will be done. So as more and more objects get into space, today you would have heard Elon Musk has a plan to put 42,000 satellite constellation to provide you internet service anywhere in the world. So that means the number of objects in space is increasing, and then many times if there is a collision which occurs, based on that, Kessler syndrome tells that huge number of small objects less than 10 centimeters also get into that. And since each of them is moving at very high speeds, they are moving at speeds like 10 kilometers per second. So even a tiny part can pierce through a panel. So these are problems. And then for again, what happens here is, like in anything, first choice is to realize some capability. Then the consequence of that capability you start worrying. So whether it is fertilizers and its consequences or plastic, everywhere it's same. So here also the initial task was to build an ability to go to space and operate. But now as things keep moving, you are getting into space debris problem, space traffic management is going to become problem. Like on traffic problem on roads, you will have traffic problem in space. All these are becoming the issues of concern, but then there are various bodies trying to look at what can be done. So some of the satellites are now being tasked, before you end your mission, you should come down and ensure you don't stay there for long. So even our stages also, if you see, fourth stage we are bringing further down before it ends operation, so that within a matter of few days or few hundreds of days, they enter Earth's atmosphere and burn out. And then there are companies which are designing how to scavenge things and how to create waste into wealth by picking up the material and reusing them. So it's a whole lot of thing which is going on.
I'd just like to give a small token of our appreciation to you. Professor Sharachandra, can I invite you up?
I'll come down there, sir.
Yes, if you could, please. Thank you. Wonderful talk. And before we conclude, could I just request everyone to come downstairs where you can see the CHG banner downstairs for a group photograph with sir, and then can all faculties come for lunch to the CHG canteen.